Hi, welcome to this recording for Unit 82. This is one of the units that is required for this astronomy class. This basically has some information that's probably a little bit outdated too. I know I mentioned a few things because astronomy and astrophysics are an ongoing topic of research. So things are discovered and at least their information is added. Some of the stuff is probably a little bit need to be reviewed and things like that. So we're going to talk about the curvature of space-time in this case, and that is basically how the geometry of space itself can dictate what we look at, the things that we look at in the shape of galaxies, the distances, and the things like that are influenced by the geometry itself. Basically, there are three options. Either the universe is flat, and it appears to be so. So when I say flat, it's not like a two-dimensional surface. Basically, the density is equal to a critical value, or it's more dense, has more material in it than the critical value. So in this case, the universe is bound gravitationally. So the gravity will win at some point, and it's going to collapse on itself. Or the universe has less material in it that the gravity will ultimately lose and the material will basically spread forever and ever and ever. This information is a little bit outdated in terms of the observations that were done in the late 1990s, and it's still an ongoing work, honestly, is that the universe is actually going to expand forever and ever because of the fact that we discovered that the universe is actually going through a second stage of Big Bang. Basically, it's really accelerated in its expansion. So we're going to talk about the positive curvature, the negative curvature, and the zero curvature. Okay, and describe the connection between the expansion and the curvature. At this point, like I said, in light of the current work in astronomy and astrophysics, these things are a little bit need to be reviewed, and discuss the effect of cosmological constants on the expansion of the universe. Again, we talked about this one in a previous unit about how the universe basically its constituents. Think of these buttons as being, for example, galaxies, and as you blow up on the balloon even if there are drawings in here, this distances between every single point in the universe is increasing. So gravity will start to weaken over time, basically, if that's the only thing that is causing it. But if there is more material in it, ultimately it's going to pull it back. That's the idea behind it. The further away the objects are, the faster they appear to be moving. So the motion is going to be proportional to the distance. Here is the point in here. If the universe is a flat, a triangle is a basic shape that you can draw from three nodes. You connect three nodes to one another to draw a triangle. The sums of the internal angles of a triangle are 180 degrees. If the universe is closed, you could end up with a scenario where this angle is a 90-degree angle, this one is a 90-degree angle, and the other one also is a 90-degree angle, in which case the sum of the internal angles they have to be more than 180 degrees. If the universe is open, it has a negative curvature. So this is a positive curvature, this is a negative curvature, this is a zero curvature. Okay, it's not curved at all. Okay, so in this case, the angles are less than 180 degrees. All of them, they are actually less than 90 degrees, and you can add them up, and they should add up to less than 180 degrees internally. So that's basically the basic geometries, okay, of the universe. That affects the size of the object that we see if the universe has a positive curvature, in other words, greater than a critical value. So in this case, things appear to be bigger because the angle with which they are sustained is bigger than if it's a flat surface. In this case, this is the actual size of the object, if indeed this is a flat universe, okay? The angular size. If it is a negative curvature, the actual angular size will appear smaller, so objects appear smaller. If you have ever experienced the concave mirror and convex mirror, you know exactly what I'm talking about, okay? look at the size of your mirror on the side of the car. It says objects appear to be closer than they are closer than they appear on the mirror, and that's because of the curvature of the mirror. So that's basically the idea behind it in here, okay? But again, which one is the universe? That depends again on the critical density, okay? Again, this critical density combined with the gravity will dictate also the fate of the universe, at least the thinking before current research in astrophysics. The idea is the following. If the universe has just the right density or less than that critical density, then the universe either will going to barely expand forever and ever and ever, or actually is going to expand for sure. I mean, if it's really a negative value. But if it has less, it has more material, basically, more gravity in this case, so the density is higher than the critical value. So ultimately, the universe is going to expand, but the expansion is going to be slowed down. In either case, the expansion is going to be slowed down. But in the case of bigger densities, then it's going to slow down, and not only the slow down, it's going to shrink again, and as it shrinks again, we happen to be probably in this phase somewhere in the expansion, and then it's going to stop and then reverse. It becomes a contraction, and then that contraction will go to a crunch and then fluctuation. This scenario now, no, it's not going to happen based in light and astronomy. Okay, this is the only outcome that we're going to be facing, and it's not probably due to the critical density, but it's critical due to another factor that we're going to mention toward the end of this unit. Okay, again, when we measure the density in this case, we take a specific typical size of the universe and then count the mass and divide it by the volume, and that's how we find the density of the universe. Again, if we measure the critical density based on the constants that are involved of the universe, we see it's related to the Hubble constant and the universal gravity. Basically, you take mass over volume, you take typical volume of the universe, you know how that volume, at least the radius of that volume, is dependent on the Hubble constant, and you do a little bit of algebra and you find this value. Now, if the actual universe of density of the universe is bigger than the critical density, the gamma m in here, omega m, I'm sorry, in this case is just the ratio of the two. The actual measured value of rho, which is the density, divided by the critical density. Still an ongoing topic, at least trying to determine this ratio. All indication appears to be of this value. Omega m equals to 1. In other words, the density of the universe is very close from the critical density if it's not exactly equal to it. But if it's more than 1, we are at the scenario of basically closed universe. We are in the scenario of big crunch. If omega m, the ratio of the critical density of the density over the critical density, is less than 1, then the universe is open and going to expand forever. Okay. If it's critical density, then this expansion will be marginal, but it's going to continue forever. This is the model that we have up to this point. Again, we know for a fact now, even if omega m is equal to 1, the universe is actually accelerating in its expansion. All of this discussion is probably a new discussion at this point. Now, when Einstein, this is the work, the theoretical work upon which this is based, he solved his field equations for the universe. Basically, the universe turned out to be a collapsing universe. The universe should not have existed at all under the laws of gravity, because immediately after the Big Bang, it should have collapsed on itself, even with those values that are known for density. So Einstein, to account for the fact that we have an observable universe that we see, he added a constant called the cosmological constant. That's how he named it, cosmological constant, just to account for the fact that we see the universe. His equations tell him we shouldn't see the universe. The universe should not exist, yet it does. So he added to his equation. Until Hubble discovered that expansion of the universe, he actually invited him in Los Angeles, and he went to the observatory, and he saw the work that they have done, and he knew, of course, about the publication. So he dubbed it the biggest blunder of his life, the fact that he added that constant. In the 1990s, when the universe was discovered to actually accelerating in its expansion, that constant is actually necessary now because it's not. Had the universe was formed from a big bang and it's expanding, it's going to continue until at some point it's going to slow down because of gravity, then that's fine. We really don't need a constant because some sort of an inertia is keeping the universe in expanding, so there is no need for that constant. But now we know the actual universe is actually expanding at even greater rate, accelerating in its expansion. So that constant is actually needed, and it exists everywhere in the universe. So that's a kind of that's the essence of the dark energy, if you have heard of it. So that dark energy is pushing against the force of gravity that is trying to slow down this expansion and causing the expansion to actually go higher. So it's in some sort of an anti-gravity energy. So that's the essence of this discussion. And that's why we know that the universe is not going to recollapse on itself, at least according to the current models. Thank you.